workshop. So. It's good. Maybe someone could remind me to pull that up at the end of class, because I was told by the administrators to leave the classroom the exact same way as I find it, and I keep not doing that, so.
You're getting in trouble for that.
I'm not in trouble. I just want to be collegial. Finley. Tristan, Annabelle. Jasmine. Victoria. Ellen, no. Lizette.
Yep.
Sierra there. Jasmine there. Rosalind. Brand, you're not here. Olivia. Jacob. Kellyanne right there. Lincoln. Emma. Jordan. That's you. And Lyle. All right, so we'll pick up back with lecture. We're about halfway through. I think it was slide 15. What you saw last, right? And if there's something that is really concerning you about first 4 chapters, ask it today. If there's something that's just not clicking, then certainly either talk about that in between the lessons, or if it's a quick question, or in sidebar with you. But I definitely want to stack the odds in your guys' favor so that hopefully you all end with A's and B's, ideally. So I think we finished this, or should I leave that up for everybody? I think it was 15. Okay, this is the new one then. Talk to me if you're trying to, right, hello. If you all walked in, you should probably just email me so I can get your attendance later. Because it's not up on Blackboard anymore, or tell me on break. This is going to be our formula. Z is equal to X minus M over the standard deviation. They're basically the same. One, we have the Greek letter mu over theta, which is the population standard deviation. And then we're actually going to be practicing doing this as well as identifying Z-scores. So this normalizes the score. And you're transforming it into a z-score, basically into a standard deviation by plugging in x, which is given to you. The mean is typically given to you, as well as the standard deviation. Or you can always use x minus m squared, and then the sum of the squares to get your variance, and then square root it for your standard deviation, which is in the formulas. You can just email me, I'll grab attendance later. That's just for everybody if you walked in late. Does not affect your grade. So we're basically normalizing scores with this formula. We'll be walking through some sample problems, then identifying how to read a z-table, which we'll refer to pretty much the rest of the term, and we'll do some practice, and then we'll walk through chapter 7. Got that? If not, tell me, I'll go back. Think you all do. So for example, we're gonna do our standard normal, we will do a standard normal distribution. A researcher measures the farthest distance in feet. The students move from the podium during a class presentation, maybe because they're nervous, or maybe they're just walking around presenting. Data were normally distributed. That just means that bell curve. Data were normally distributed. So it's literally, just for review. So literally just saying that data were normally distributed, just bell curve. With the mean at 12, standard deviation at 2, what is the score for x equals 14 feet? It always helps if you sketch it. So if we're sketching this, I feel like this is not that great of a marker. Any better? Not really. Okay, thanks for being honest. I steal them from the adjunct office and the chief academic officer at work, so a lot. This one's probably better. Is that better? So our mean, which is gonna be right in the center, that's 12. And the standard deviation is 2, 14, 16, if you're trying to sketch it out. 10, 8, 2 to left or right. That's your standard deviation. So what is the score for x is equal to 14 feet? So remember, we have z is equal to x minus m over the standard deviation, basically the same formula, which means it would be z is equal to 14, because that's our x, minus m, which is 12, divided by the standard deviation, which happens to be 2. So if we do our top, that's going to be 2 divided by 2, z is equal to 1. Pretty sure that's what the next slide says. No, no. So literally what I was, were you guys still writing? Are you still? It's because m is, the mean is 12, standard deviation is 2. Find the z-score by substituting x into 14 by substituting the values into z transformation. And then this shows you visually what that looks like with that sketch. Z is 1 standard deviation above the mean. So you're basically normalizing the score and calculating where it would fall based on the x value. See that. Do you have that so far? Is that making sense? Not making sense? Need a few more moments to write? A minute or two, or you all good? This is the unit normal table. This is absolutely in chapter 6 as a PDF. It says Z table. Your Z area and your Z value, okay? Area between the mean and the Z, which is this, mean to the z, that standard deviation we just calculated. Area beyond the z, right here in the tail, we're gonna start calculating what's under the curve. But just formulaically, like we'll be able to just plug the formulas in. This week, it's more that, and then I think as we get into 7, it's a little bit like testing hypothesis where we see where it is below this as to whether or not it's false or true for hypothesis using math. So you make an assumption something is or is not working, mathematically calculate that based on the data that's given to you. So there's absolutely a real world application coming up. This week is a little bit of just the z-scores. But the helpful z table that's in chapter 6, we'll be referring to that. And there's other stuff like t-scores and f-scores that are coming up, but don't worry, we will walk through the density of the material. It'll all be in that original z table in chapter 6. Yeah, I think it's z-scores and then t-scores, but the formula is almost the same for 6 and 7. So that told me. So here's our breakdown of what the scores mean. If I need to go back a slide, just talk to me. Column A, list z-scores, only list positive z-scores. A negative z-score is equivalent symmetrical distribution. So a z-score of 1 or -1 would be the same thing. It just depends on what side of the mean it's on. So if you're referring to a z-score, you're just going to use a table, whether it's positive or negative. If you're trying to look up a proportion or something, you just use the positive version of that. Column B lists the area between the z-score and the mean. First value is 0.0000, which the area between the mean and z is equal to 0. As the z-score increases, it moves away from the mean. The proportion of the area between the mean score increases closer to 0.50000 because mean, 50% of the data, 50% of the data, that's at 0.5. All of this is 1 or 100%. That's where that comes from. Column C lists the area from the z-score towards the tail. As the z-score increases, the area between the score tail decreases closer to 0.0000. Sorry. I tried to make noise. That sounded like that was like chalkboard. Sorry. We have so far? Yes, no? So looking at proportions. Area D score given as a proportion, that's in our unit normal table you just referenced. Again, chapter 6. Z score, locate proportion of probability for the score. To locate proportion, transform the raw score into a Z score. Locate the corresponding proportion for the Z score in the unit normal table, which is literally just cross-referencing it, which we'll walk through the math today. Sketch to make certain and understand negative and positive areas. Yeah, that's so far. Yes. Okay, cool. So this is an example of locating proportion between the two values. So data indicative of chewing gum improving academic performance by scores and standardized math test of 20 plus or minus 9 points. Mean plus or minus standard deviation. If you see that, that's literally your cue to think mean plus or minus standard deviation. Assuming the data are normally distributed, bell curve, what probability that student who chews gum will score 11 points first time and 29 points the second time, like more points from chewing gum? So we're walking through the math on how to do that.
Which one would be the mean?
We're going to use the X formula, the Z minus X
Ah.
minus M over standard deviation twice. And then that's going to tell us what that looks like because we're going to look at the proportions. That's literally what's going to be on the next couple of slides. So we'll look at the probability of whether or not the chewing gum will make it increase by that amount. That's what we're looking at. So here's our first one. So for x is equal to 11, we're going to plug that in. So 11 minus 20, x minus m, that's our mean, over standard deviation, which is 9, -1. So we're going to look up the z-score in column B of appendix B. Look at B for the proportion between -1 and mean, p is equal to 0.3413. Now, that's in your Z table under chapter 6. When you're done taking notes on this, I can absolutely show you on the screen where that came from, so it's not just like you're wondering. And then to find the portion for those two scores, we're going to add this later to whatever this value is, x is equal to 29, because we're looking at the probability of both things happening, which is why it's cumulative. Both the 11 and then the 29. Was probably of it increasing by 11 points and then later increasing by 29 on the second attempt. We have that. Yes, no. So for x equals 29, same formula. -29 minus 20 divided by 9 is 1. So we get the same proportion again, which if you're wondering where that came from, if you go into the helpful z-score table right here, here's our z. Our z was 1.3413 area between mean and z. That's where that came from. That's where they're getting these numbers from. So we add those together and we get 0.6826, about a 68% chance or so of the thing happening. because the six make it a 6.683, and if you were rounding, you round down, so about 68%. If you were making that into a percentage. But the exact probability to be 68.26%, or then again in the decimal form of that happening. So pretty good odds. You're still pacing fine, but towards the end of class, it might change into doing worksheets and you guys taking notes on your own on the slides, just for time's sake. Not yet. I think we're still okay. But I have worksheets with like all the notes on them when the math is harder. And we might just do those towards the end just so that we have extra time to walk through everything. I think we're still okay because we're going to be through 7 today and then 8, 9 next week, 9, 10 the week after, and then 11 and 12 in the same. So that's why I'm thinking leaning into just worksheets in the relatively near future is probably going to be pretty important. So you didn't know until we used to look at scores. I need to go back. Just talking. Yeah, just like you're good. Thank you for telling me that. Score right here. Okay, if you are. So locating scores, unit normal table can be used to locate scores that fall within a given proportion or percentile. Locate the score, locate the z-score associated with the given proportion in the unit normal table. Transform the z-score into a raw score x. Step 3, take z times the standard deviation plus the mean. Yeah, so far? Yes. Okay. So locating scores continued in a general healthy population. IQ scores are normally distributed 100 mean plus or minus 15, mean plus or minus standard deviation. Assuming these data are normally distributed, again, bell curve, what minimum scores needed to be in the top percent of the distribution of intelligence scores in its distribution? So we're going to look that up in the Z table. So go into our Z table. So beyond the tail, that's what they're getting. I think it's 1.27, 1.28. So that's being pulled out of here. You guys see that okay? Point. That's as close as we can get to 10%. It wouldn't be this one, that's a little bit higher. And it wouldn't be this one because that's below. So because that's really close, we're just doing slight rounding. Because most of the, like to the 100th place makes sense, to the thousandth, it's really close. So that's where that's coming from. So top 10% is 1.28. And we use the Z transformation to solve it. So someone has an IQ greater than 119.2. That's the top 10% of the intelligence scores in this distribution. And we're going to walk through the math entirely, like where they got that from. So step one, top 10% of scores, same as P is equal to 0.1000 towards the tail. That's in your Z table. To locate the Z score associated with the proportion, look up for P is equal to 0.10000. In column C, which we just did, So Z score is equal to 1.28. If that sounds like Charlie Brown's teacher, just tell me and I'll go back to the Z table in chapter 6. Z score is equal to the 1.28 cutoff for the top 10% of the data. Is everybody with me so far? Did not just pull that number out of the air. That doesn't make sense. Read your face. Perfect. Thank you for doing that. Okay. This right here, this is our Z table. This is column C. This number right here, which is the area beyond the Z and the tail, we went over and we got 1.28, which is in column A. That's our Z score. That's where that came from. We determine which score X in the distribution shown in figure 6.11 corresponds to the Z score equal to 1.28. Since Z is equal to 1.28, you can substitute this value into the Z transformation formula. Z times standard deviation plus mean 1.28 times 15 plus 100, or 1.28 is equal to X minus 100 divided by 15. Everyone have this before we go to the next slide? Yes, no, talk to me. Okay. So multiply both sides of the equation by 15 to eliminate the fraction. So z times standard deviation plus 15 is equal to 128. Times 15 plus 100 is equal to 19.2. So you divide, get rid of that. 19.2 is equal to x minus 100. Therefore, you add 100 each side of the equation, and x is equal to 119.2. Score equal to 119.2 on an IQ test is a cutoff for the lowest score in the top 10% of scores. That was so fun. Yes. Go back just time to me. So going from binomial to normal. Distribution of random outcomes. Binomial variables referred to as binomial distribution. Binomial probability distribution is distributed with the following formulas. Mean is equal to NP, or standard deviation is equal to the square root of NPQ. N is the sample size, P and Q are the probabilities for each binomial outcome. Typically, they're going to give you some of the probabilities so you can plug that in and do the math. Typically, You're typically not going to see it where you don't have enough stuff to plug it in for each. Going from binomial to normal, you need to go back, just talk to me. Binomial distribution approximates normal distribution, so as long as n is greater than 2 or equal to 2, that's the greater than or equal symbol. Otherwise, it doesn't work. The larger the n, the more closely it approximates normal distribution. So the closer it approximates this. So that means normal distribution can be used to estimate binomial probabilities when np and n and q are greater than 10. When n is equal to infinity, binomial distribution is theoretically perfect normal distribution because n's infinity. So suppose you select two participants, where he has this? Yes, okay. Suppose you select two participants from the population with equal number of men and women, random variable X, number of men, sample two participants, three possible outcomes, 0, 1, and 2. So sample space and relative frequency distribution, suppose selecting men from a population with equal number of men and women. So normal approximation binomial distribution, assuming NP and NQ are greater than 10, binomial probabilities can be distributed along a standard normal distribution, just bell curve. Check for normality, again, bell curve. Compute the mean and standard deviation. Find the real limits. Remember, real limits for the upper and lower values within which probability obtaining that outcome is contained. Real limits for binomial outcome are x plus or minus 5.5. Locate the z-score for each real limit, and then find the proportion located within the real limits. So this is what this just looks like graphically. P is 0.0414, real limits from 30. 29.5, 30.5. Mean is 25, number of male samples is 30. You guys ready to practice? So we're gonna have this so far before I move on to the next thing. So, you can leave it open for a moment, we're fine. We're still pacing okay. We're about halfway through. We have about 11 hours left together. So like I said, we might have to do worksheets and less PowerPoints. You might have to start taking notes of the PowerPoints on your own. But my worksheets that are coming up are incredibly detailed. So I think, like right now, we're still pacing fine, but I might just focus on walking through the math just so we finish on time, because I looked, we don't have a final day. 8/7's it, which means we have this time, we have this class period, next class period, and the period after that, and that's it. We will get there. My worksheets are really good. I'm trying not to have to put you guys in any like, hey, watch the recording. So thinking I might say for next time, do your own notes on these upcoming chapters. And then I just walk through the nitty-gritty of the math.
You say 8/7 to be 11.
8/7, we're done.
8/7's a Thursday.
So we're done on
4.
8/4.
Okay.
Oh.
That doesn't make sense.
So that's 21st, 28th, 4th. And we're about halfway through, so we might have to go at like 2 chapters versus a chapter and a half. The worksheets that I have as it gets more and more dense and thick are actually very extensive. I created them by hand a couple years ago. It's just that the PowerPoint and taking notes, you might have to start to skip that just because it's accelerating. But I don't want you guys to feel lost. I want you to ask questions if you're stuck along the way. So I might start saying like, hey, take notes on these couple PowerPoints, come to class with your notes, and then just walk through the math. So we should keep sharing and share screen. So let's go into Blackboard. And we're going to do student resources. And we're going to go back to our in-class activities, and we're going to do the part B that we did not finish yet, which was that part 3. This can we do next time. So what we're going to do is we're going to notice that there's 3 columns. We'll locate each one of the norm table and write down the values you see in columns B and C across from it. You guys want to do that together, or do you want to do that on your own? What's going to help you the most? Talk to me. Do it together. So this one right here, 0, you're going to go into student resources, and you're going to go to chapter 6, and you're going to click on the Z table, and we're going to find it. And you know what? It's right there. Does that make sense? Where I got that from? So this one is literally like those would be your answers. Our next one, we look up the 1 as though it was positive. You with me so far? We're going back to the Z table. So we're going to find Z1, Z as 1, and that's right here. So it's these other 2. That's your B and C column. Right there. 0.99, same thing. It's these 2. That's your B and C column. Everyone see that okay? Know where I'm getting that from? I want to make sure the pace at which I'm explaining it is making sense for everybody.
Where do we find the appendix?
That's in chapter 6.
Chapter 6.
And it says helpful Z table. It's right here,
Oh,
helpful
right.
Z-score table. So can anyone maybe tell us what -165 is? Look up like it's positive. What are our numbers?
So 0.4505 and then 0.0495.
Yeah, right here, nailed it. Yep, right there. Want to see where that's coming from? We're just looking up Z-score tables. All we're doing is finding the Z-score?
Yeah.
Just look at that.
I do, yeah, I do.
You didn't know anything about that. This
Oh, this.
Z-score table.
Okay.
And then scroll down. We're literally just finding the Z-score and doing the two columns to the right.
And then the form that we're gonna request that's on chapter 7, what?
This is last week's date, part B.
Okay, so yes.
This is the third part of it. We scroll down on the probability worksheet. I can show you that. It's right here. It's student resources, in-class activities, and at the top, part B on the homework.
Okay,
And then this file right here, you just hit it, the blue to download it, and then you're looking at this, and all I did was scroll down to part 3. So 1.65, if we go back to our Z table, is right here. And it would be these two, which I think Justin had just pointed out. Should be those two. And then 1.96 would be right here, and it'd be these two. We're just listing the scores, just getting your feet wet with the Z table. That is the rest of that worksheet. Yeah.
can you show where -1,
There is no negative.
1.0?
It's always look at like it's positive.
Okay.
So you're finding the 1.65 in the Z table.
So how did you?
Can you show where that is? So let's go down a little bit more. And then 1.65, and those two numbers right there, that's your B and your C column. Look it up, it's a little bit.
Oh, this one. No, I was talking about this one, sorry.
So that's one, so you just scroll back up so you find one. Right here's your one. And then it's, you know, you go past one, yeah, this is one. What's one, and then it's those two. It's your B and C, which is the same. One. Yeah, and the area beyond the Z and the tab.
For all of these.
Just the Z and then.
Thank you.
No problem. So then you can just submit that. So I think it's up here. Where is it? Is this it? Yeah, that's probably it right there. Edit. Sweet. Move this, make available. And then we're gonna move this up. And probably just the activities. So you're looking for in-class activities. Because that was the end of that worksheet. You can just submit that. This week, and you're looking at chapter 6, this is review Dr. Mac. And then enable editing. So we'll just start with example one. Or we can walk through the notes. Walk through the notes again, would that help everybody? Or just the examples? Walk through the notes? Maybe. The notes, okay. So the normal distribution, also called the symmetrical or Gaussian bell-shaped distribution, that's that normal curve. So we know where this is, by the way?
Yeah.
You're gonna go to in-class, so student resources, in-class activities, today's date, and then chapter 6 review. And you get a downloadable file this week, and it should look like that. I can come around if you'd like, or I can show it to you again. Student resources, in-class activities. At the top, you should be able to see the folder with today's date on it. We're just working on the chapter 6 review. That's it. And that looks like this. Does that make sense? You find it okay?
Yeah.
Part B, are we putting in under the thing that says homework science 725 part B?
Yes,
Oh.
100%. Yep. Everyone able to find the worksheet I pulled up? How's the energy? Should we take a break? Should we take a break in 10? What's good for you guys? I try to go about halfway, just trying to read the room here. 10 minutes? Okay. Walk through the notes, right? Worksheet, probably. Okay. Definitions, FYI for your review. The normal distribution, also called the symmetrical or Gaussian or bell-shaped distribution, is a theoretical distribution in which scores are symmetrically distributed above and below the mean, the median, and the mode at the center of the distribution. FYI, most behavioral data approximate a normal distribution. Rarely are behavioral data exactly normally distributed. So again, that's just all bell curve. In a normal distribution, 50% of the data fall above the mean, the median, and the mode, and 50% fall below these measures. That makes it a bell curve. That's the mean, above and below the mean. In a normal distribution, the mean can equal any value plus or minus infinity. The standard deviation can equal any positive value greater than 0, because it's the standard deviation moving away from the mean. Proportions of the area under a normal curve are used to determine the probabilities for normally distributed data. The tails of a normal distribution never touch the x-axis, so it is possible to observe outliers in a data set that is normally distributed. The standard normal distribution is one of the infinite normal distributions. It has a mean of 0 and a variance of 1. The Z transformation formula converts any normal distribution to the standard normal distribution with a mean equal to 0 and a variance equal to 1. A Z-score is the value on the x-axis of a standard normal distribution. Numerical value of a Z-score specifies the distance or number of standard deviations that a value is above or below the mean. The standard normal distribution or Z distribution is a normal distribution with the mean score equal to 0 and a standard deviation equal to 1. The standard normal distribution is distributed in the Z-score units along the x-axis. The formula for the Z transformation can be found at the top of page 180, approximately in our text, or 6.4 in the electronic textbook, give or take, because they change the page number sometimes with new editions. This is the whiteboard formula. Boy, it's just my cue to not miss it. So, a researcher measures the farthest distance in feet that free throws are made during basketball practice of professional basketball players. The data were normally distributed with m is equal to 10, mean, standard deviation is equal to 2. What is the score for x equals 16 feet? So we're going to plug it in. Because m is 10, standard deviation is 2, we can find the score for x is equal to 14 by substituting these values into the Z transformation formula. 16 minus 10 divided by 2 is 3. Those numbers make sense where they came from. This should be 16. There's a typo. Yeah, I got it. 16, x is 16, this is 16. Make sense? That's where they came from. Dr. Mack's not perfect. Sorry, my bad. By substituting these values into the Z transformation formula. 16 minus 10, okay, that was our mean. That's x minus m. Divided by standard deviation of 2, which was given to us, is 3. Therefore, a score of x equals 16 in the original distribution is located at z is equal to 3 in a standard normal distribution of 3 standard deviations above the mean. So if you're drawing that, like it says, you would have draw a bell curve. That are normally distributed with the mean. So here's your mean. 10. And standard deviation was 2. So that's 12. 14. 8. 6. That's every one of those is a standard deviation of 2. And what is the score for x is equal to 3 feet, to 16 feet. And the z-score, it would be 3.03 standard deviations of the mean. So when it's x is equal to 16, we're still going to have the same mean, which is 10. And it would be 3 standard deviations, 13, 16, 7, 4, x. This is because z is equal to 3 when x is equal to 16. Is that making sense? That making sense? So now, assuming these are amazing basketball players, let's calculate x is equal to 20 using the exact same formula. How would we do that? So we want to give it a shot. But try it on your own, you want to work together. How will it help you all the most? Okay, can someone guide us? It's not just me. If you're really not feeling that I can guide us, it's no problem. So let's walk. So what do we always do, right? We do z is equal to x minus m over the standard deviation. Do we have that information? We have x, right? Z is equal to x minus m over standard deviation. So z is equal to 20 minus, I think our mean was 10, right? And our standard deviation was at 2? It was 2. So 20 minus 10 is 10 divided by 2, therefore z is equal to 5. Does that make sense? We're normalizing that. Because I have freedom, how about you don't have to create your own scenario? Always delete that. So we just plugged it in. X is so we had when x is 20, we plug it into the formula. This is our x right here, minus m, which is our 10, over 2, which is our standard deviation. Therefore, c is equal to 5. The numerator and the denominator. We're normalizing score. That makes sense. That's the answer to that one. Should we keep moving or should we walk through that again? Keep moving. Okay. The unit normal table or z-table is type probability distribution displaying a list of z-scores and corresponding probabilities or proportions of area associated with each z-score listed. We were literally just referencing that. Estimate probabilities under the normal curve. We determine the probability of a certain outcome in relation to other outcomes. The steps for locating proportions are as follows. Transform the raw score into a z-score, raw score x into a z-score. Locate the corresponding proportion of the z-score in the unit normal table. Example, A sample of scores normally distributed with M is 10, standard deviation is 2. What is the probability of obtaining a score greater than 14? So our math changes a little bit. The shaded region in our Boolean figure 6.6 represents a proportion or probability of obtaining a score greater than 14. We apply the 2 steps to find the proportion associated with the shaded region. Step 1, transform the raw score x to a z-score. We compute a z transformation in this example. X is 14. The z transformation is 14 minus 10 divided by 2. Therefore, 14 minus 10 is 4. So 4 divided by 2, z is 2. You can see the formula on page 184, or approximately section 6.6. And then you take one to draw it like that. But label it accordingly. Does that make sense, or is that not making sense? I can draw it. Really lost here. So we have 2. So step 2, in this example, we're looking for the proportion of z is equal to plus 2 toward the tail. To locate the proportion, we look in column A in appendix D for a z-score equal to 2. The proportion towards the tail is listed in column C. The proportion greater than 14, the original distribution is p is equal to 0.0228. So how do we get that? We go back into our student resources, chapter 6, helpful z-score table. We're going to find 2 right here beyond the tail, 0.228, 0.228. That's where they came from. So the probability is 0.228 of obtaining a score greater than 14. Therefore, listing this in percentage would be 2.28 because you move the decimal over 2 places to say the percent. So now to the following problem on your own. I'll just get rid of the scenario of your own because academic freedom's awesome. How about that? A sample of scores is normally distributed with m is equal to 9 and the standard deviation is equal to 3. What is the probability of obtaining a score greater than 18? Please show your work. So we're literally going to do the same thing. We're going to take the z transformation and we're going to get the z-score and then we're going to look at the probability. So z is equal to x minus m. So z is equal to 18 minus 9. Does that make sense? Where that's coming from? Should I write it on the board? 18 minus 9, which is going to be 9, divided by 3. Sorry, z-score is 3. And then we cross-reference that in here to 3, which is 0.0013 for probability. Because it's towards the tail. We're looking up, which means it would be 0.0013 or 0.13% if we were to make it a 0%. And the total area is 0.500 above the mean and 0.500 below the mean. Should we take 10 minutes and then do the next couple of problems? We're kind of like halfway through. Is it clicking? Is it making sense? I said it out loud, didn't read it, say it on the board. It made sense to everybody.
Mostly,
Mostly.
yes.
So remember,
The formula, if you just pull up the formula again.
it's always
Z
is equal to x minus m, which we did 18 minus 9 just now, which literally gave us 9. And our standard deviation was 3, which is why z was equal to 3. And then we looked up z in the table, and we looked at column C, and it was, which is the towards the tail, which is p is equal to 0.0013 or 0.13%. Because if you multiply it by 100, you move the decimal over 2 places. That's where they came from. To make it into a percentage. So we just cross-reference the table to get to that. Yeah, we'll do the rest of this when you guys come back. We might just do a worksheet for 7 just to keep pacing. We're probably going to have a class or 2 where there's like 2 or 3 chapters because 12 is dense. And I want to make sure we get to put lots of practice for 12. So when you talk about F scores, it's not the hard part on the test. I can't guarantee you'll be fine, but generally speaking, you will be fine. Like very close to a guarantee because I've had a lot of success with this course, with feedback from you all saying that I break it down and it's clear for you. I just can't promise that will happen, but I feel pretty confident it will. Because it usually does. So I'll see you at like quarter till. Take 10 minutes right now. Let it like sink in, do something non-math related, etc. And then we'll talk in 10 and finish up the worksheet.
Does the teacher need a break? I just want to pick your brain.
I do need a break. I do need.
No, that's why.
I need like at least a bite of
See?
some water all day.
Yeah.
So the number that we formed after doing that, so after we do the X minus S, that's just that we get on the top, the bottom, so the reason why it's. But let's say that we find in this case.
So.
No, because we get it in the rate.
Yeah. My computer filed.
And it's like.
Oh, I've been trying to read it little by little, to believe.
The mean for what there's going on, which it tells what.
Right.
You know, right? Yeah, it's just.
Because we're gonna,
Yeah, see?
we're gonna,
Oh, yeah, so this is the form.
we divide the by the bottom. You divide those two numbers.
Yeah, because that was the.
That number is you find on this table, and then it correlates to different numbers. So since we.
Because it's out of,
Three there.
because this is the same formula, it's out of the same scores, so 18 is the sample in this one. So then if that number was like 26, then it would be 26.
Okay, it's just a wording, it's wording.
Yeah.
It's really wordy.
I know.
Wordy, it's something. So that
I know.
Okay. Well,
In
yeah,
between,
more than that.
mean and take real quick, what's only feel us, like what's.
So then.
This one?
It's 95. Okay, okay.
That's what I get, if I'm wrong,
Thank you. No, that was, I'm gonna ask him, would it be 100?
Yeah.
So that makes sense that 18 would be
just a plug-in number.
a plug-in number.
Yeah.
It's, there's no other information that's saying 18. I know he said something about going to the table, but.
I think that's to reference it in, like, as you solve it, because normally for the equation earlier, we got like -1 or +1, so I think it's to compare it, like, if that number does become a decimal, maybe using whole numbers. Wait,
Okay.
I think that's where that came from.
That's where he was mentioning that. Yeah, sometimes you slow down.
You're good, it's so wordy.
That number equals one of the numbers. Yeah. One of those extra.
Too long.
And then when you find that. Give us.
You know what I mean? And because they were in class, with this school use. You know, like sometimes. So then you just say that, and then three examples.
Yeah, there's
Sign up.
Oh, absolutely.
Then you divide.
So he doesn't have a class video, slides into them, plug it into this. It's kind of like an AI situation where it summarizes it and breaks it down without all of that. I have to get the name of it from him, but if I get the name of it, I'll send it to you because it's been really helpful for his stuff.
Yeah.
He's pre-med and he's like, you know, I can hear. He's really hard of hearing.
Yeah. But if you have something that's right.
It's
And
yeah.
cutting it down to the.
Yeah,
Yeah.
he's got it somewhere. I gotta ask him about it.
Is it something
If it does, I don't know. I also think it might be one of those ones where if you sign up for like a free account, you get the bare bones, but like you don't get as much examples out of it. Like, you might get one or two, something like that. I don't know. He's been experimenting with it. Classes started a week
It's
ago.
worth a try, right? I mean,
Yeah,
anything at this point.
it's also one of those things of. I thought about just see, I can put on closed captions and just read it, like the transcription from his videos, but it's not published on YouTube or anything, he's recording it separate. So we can't just get the text out of it. Cause that's normally what I do when my teachers put on lectures, cause a lot of them from COD, they put it through YouTube,
Yeah.
so then I just read the transcription.
That's it.
Yeah, if it,
But-
if it.
But if it'll work.
I don't know if he puts them on YouTube or if it's just he records it through whatever and then puts it on Blackboard because they don't automatically do captions on some stuff.
Gotcha. Yeah, no, that's, it was a great. And even, you know, depending on the cost, it might be a little bit.
Oh,
Yeah, thanks. I'm gonna grab my,
So what do we do? We're gonna finish just keywords and there's way too many words in the sheet. Half of them are just explaining. Yeah. Where do you?
Oh. I really saw.
So anything that's stated in black. Everything else is just examples. Just it's a step by step one. Isn't that very celebration to you? And I really see it. Well, so we're- And from, and we're big, and see, so like, we live in place, but we'll see, and it's. Guess you're great, but. Already have speed. So, and, and, so that's why we know that, and this big thing. All the, street. So I'm pretty sure it's the exact location. Not that organized, that's what we really organized, correct? Yeah.
You can fight yourself out.
What was that?
Someone's ever done. They just fight themselves out. You asked me.
We're gonna let you in.
Thank you. Appreciate it.
And we're gonna let anybody else in too, just as long as there's noise. Yeah, so. I reported that. Well, you didn't do the SPSS thing. Because there's, oh wait, but then what's that?
That way.
I didn't think I said it. Just, can you email me? Or can you
Just give it to
Can you just email me the same thing? I don't think it'll.
So I just need that discussion. They know all that. So. You should just hand it over.
Yeah, we're looking at, so we were for the one we just did, we're looking at C column. These, the one you just showed me, it's just the beginning of the
Yeah.
sentence from the C source.
I'm zero.
This one's C
Nice to meet you.
for the for the probabilities that we were looking at. Home exam. The one that you showed me, just kind of basically get familiar with the Z score, B and C. This one is specifically for
So probably
C,
get
just
that.
area beyond.
Oh,
This.
yes. Okay. Thank you.
Okay. Appreciate it. Thanks for letting me know. We had this one, I thought I missed it. but-
We'll take you through this one.
Oh, right. It's too much.
Oh, someone.
You got it? Okay.
Does it lock immediately?
I think it does, but we're gonna let them
Yeah,
in.
it's immediate. Are we sure? Sure. Usually.
I've been known not to at my day job, but that's different, so. Are you guys ready to jump back in?
Yeah, my only question was the 18. You got it from the probability question, right? That's what the 18. came.
It was, yeah, it literally was given
That was all I needed. Thank you.
to us, yeah,
Okay. Perfect.
it was right here, it was 18.
Perfect.
All right, so a practical application, can you guys see, okay, should I zoom in? The sales team likes to send funny jokes around the office to break up the monotony of making outbound calls. Not the job that I left, this job. At all. The manager wants to, totally is, the manager wants to know how mindful his or her employees are of staying on task. The manager actually got in trouble with my director for wearing too many Hawaiian shirts too many Fridays in a row, so I wore more of them for days. The manager develops a survey to track how often employees are off task. She reports they spend an average of 6.4 mean, plus or minus 2.4 standard deviation off task during the day. Assuming the data are normally distributed, what is the probability that employees in this study spent less than 8 minutes off task during the day? Like, did the jokes work? So step one, to transform an X to a Z score, we compute a Z transformation. In this example, X is equal to 8. Therefore, Z is equal to 8 minus 6.4, X minus M, over 2.4, which is equal to 0.67. Everyone with me so far? Yes, no? Okay. In the distribution example, 6.7, time equal to 8 minutes is located 0.67 Z-scores, or just over half a standard deviation above the mean in a standard normal distribution. This is not the exact picture shown in the book, but you can draw below it using it as a frame, but accounted for 8 minutes. In this example, we are looking at the proportion from Z is equal to 0.67 back to the mean, and then we will add 0.5000, which is the total proportion of the area below the mean. So we're thinking about this, the proportion below the mean. To look at the proportion, we're looking column, got back and spell today, A, in appendix C for a score equal to 0.67. So if we look up the Z-score, 0.67, it's 0.2486 because we're looking for between the mean and the Z for this scenario. So that's 0.2486. So we're going to add that to the other half of the mean. So the probability is now 0.7486, or almost 75%, that employees spent less than 8 minutes off task during the day, which means the funny jokes are the opposite of the monotony of calls was actually working, mathematically speaking. Does that make sense? So now using the same formula, calculate in the same steps, calculate the likelihood, and we'll just go like that for you guys. Okay. Calculate the likelihood that employees spent less than 10 minutes off task per day. Please show your work and create a normal distribution in the shaded areas you're calculating. How about we'll just say, please show your work. So let's work for you guys. Should we do this one together, or do you guys want to give it a shot? It's the same formula above. Do it together? Is that the look I'm getting, or you guys want to give it a shot on your
Oh,
own?
it's together, but.
We can do that. My only concern is that if I walk you through it, you're like, yes, it makes sense. And then you get home and you're like, I never practiced this. We can do it together. It's fine. Should we take like a few minutes to give it a shot? And then I'll walk you guys through it, like 3 to 5, 5 to 7, something like that. And then I'll kind of see where you guys are at. And then we'll do that.
I've just been reading.
No, because you're not plugging the 10 back in. We're doing this right here. Because we said 10, x is equal to 10. This is right because of that. Go back to this one. That's where you're on. Yes, like 432. Don't scroll. In this type of scenario, yes.
Yeah.
Okay. Yeah, so we're trying to see. If that scenario is happening, that's when we add it back.
Okay.
To.
Yeah.
What do you got?
Yeah.
Yes. Let me see. Okay. Did everybody get this? You guys want to walk through it?
Yeah.
Yeah.
Take a look through.
All right. So we're gonna do x is 10, right? That makes sense? X is 10. So we're gonna plug in z is equal to x minus m. 10 minus 6.4. Do the numerator first. You should have 3.6. Divide 2.4 into that, you should have 1.5. That's your z-score. Then you're going to cross-reference your z-score to our z-score table. And you're going to look in column B back to the mean, which is 0.4332. Going with me so far? You want to see where I got the 4.332 from? Anyone? Yes? Okay. That's right here. Area between the mean and the z. 1.5, 0.4332. Those are probability. So we have that, but we have to add it back to the 0.50000, which is the total proportion below the mean. We have to account for this in this scenario. So we add those two together and we get 0.9332, or about 93% chance, again, that it's working because they're off. They spent less than 10 minutes off task. Like it's increasing. The likelihood of them spending less than 10 minutes off task is going up. So like they're working. Like they're off task more when the number's lower. That means the funny jokes around the office are working, mathematically speaking. You got. Because that's half. of this. This is 0.5000 and this is 0.5000, and we have to account for below the mean to add to it in this scenario. That's why it's 0.993.
Is it always gonna be 0.5?
Yeah, if you have to, if you're accounting for that in the problem, absolutely, yeah. You don't always account for the problem, this type of problem you would. Because it's the less than thing that we're thinking about. So you have to add the up to that point plus the other probability. As a cube. Does that make sense? So locating proportions below the mean. If you have questions, please do ask. In the standard normal distribution, z-scores above the mean are positive. Z-scores below the mean are negative. Because the normal distribution is symmetrical, probabilities associated with positive z-scores are the same for corresponding negative z-scores. We went over that from the lecture. A z-score is a z-score. Researchers are often interested in depression across many different groups, which can be measured using the Beck Depression Inventory. Individuals who experience chronic pain are one such group for which depression is of interest to the researcher. Using data based on reports and published research, suppose a group of veterans experience a chronic pain score 24.0 plus or minus 12 on the BDI-2, where higher scores indicate more severe depression. According to conventions, a score of 13 or less is regarded as a score in the minimal depression range. Assuming these data are normally distributed, what is the probability of veterans who experience chronic pain score to the minimal depression range 13 or less? So this is locating proportions below the mean, not from the mean and beyond, below the mean. So that changes our math. So to transform the score into a raw score, the raw score x into a z-score, we compute a z transformation. In this example, x is equal to 13. Z is equal to x minus m, that's that mean, divided by 12. 11 divided by 12, which is negative, which is point. Yeah, because that would be negative. This would be a negative. That makes sense. Point negative 92. So we're going to look up 0.92 below the mean. So we look in column 2 and where's it? 0.92. 0.92. And because we're looking at the area beyond the z in the tail, because it's less than, that goes up to that mean, that's why. Look at this, we're thinking about this now. This is below, that's why we're doing that. So the proportion is 0.788. Therefore, the probability is 0.788 that a veteran given this depression measure scored in the minimal depression range, a score of 13 or less on the BDI-2. Now, assuming the data in a new group of veterans is 26 plus or minus, mean plus or minus standard deviation, on the BDI, calculate the score in the minimal depression range. Probability of veterans with a score of 15 or less, assuming in this scenario it's 15. So you use the same Z formula, and please show your work. So all we have to do is take this and just make sure we plug our numbers in correctly, and it'll work. So x minus m. So we know that that's so they scored a 15. So that'd be 15 minus 26 divided by 11. Does that make sense where those came from? This is our standard deviation, so that goes here. 15 was the x score. So just should say 15, that's just say cut and pasted. And 26 is our mean. That's where that's coming from. So can someone tell me what that would be? 15 minus 26? Made 11 divided by 11, right? So that'd be -1. So our P is gonna change, right? So we're just gonna look at one back here. Our probability. So one is 0.3 is 0.1587 because that's beyond the tail. Therefore, if we wrote it out, it would look like that. Does that make sense? How we got there? Want to see that again? Yes, no? Okay. Example 2. Memory is a factor often studied in patients with trauma, such as a stroke, in which it is possible that memory is impaired. One type of metric used to measure memory among stroke patients is the COD, which includes a series of tests with a higher raw score indicating more severe impairment. User, not use data, user data, based on reports of published research, suppose a large sample of stroke patients scored 7, mean, plus or minus standard deviation 2.5 on the COD metric. Assuming these data are normally distributed, what is the probability that a stroke patient in this sample scored 4.1, there's our X value, or higher on this metric? So 4.1 minus 7.5, X minus M, divided by 2.5, standard deviation, 3.4 divided by 2.5. This is going to be a negative because 4.1 minus 7, that's where that came from. So we get a negative 1.36 for a Z-score. So we're going to look this up, but we're going to add 5 because of our verbiage here. Because if you go back and look at what we're asking, or higher, not less than, that's our Q. That's why we're going to add the 0.5000 back to it. That's how you know. So we're going to add our probability of the 0.4131, which if we go back to our score, which was 1.36, right? So 1.36, 0.4131, because that's between the mean and the Z score. And then we're going to account for the other half, the other direction. That's why it's a plus 500, because it says right in here, that equal, that should be deleted. Or higher. So we're saying it was here or higher. That's why we have to add it, because we're accounting for the rest of underneath the curve. So we add the 0.4131 to 0.5000, we get 0.9131. The probability is 0.9131 that a patient in this sample scored 4.1 or higher on the COD metric. Now using the same sample, calculate the following formula. 8.5 plus or minus standard deviation on the COD metric, that they scored 6.3 or higher. So you just take, all you have to do is take this and literally make sure you add it back together the correct way. You have your answer. But it's going to change. So it's 8.5. So that's our mean. So that's what we're going to subtract. That's our X minus M, 8.5. Our standard deviation is going to be 1.5. And our 6.3 minus 8.5 is negative 2.2 divided by 1.5 is 1 point. I get Z is negative 1.46 or 1.47 if we round. So this is 1.47 Z scores. So all we do is look that up, 1.47, which is 0.4292. So we're going to add this. And this is 1.47. 1.47. So we would add 0.4292 plus 0.5000, and we would get 0.9292, which would be our probability. Everyone see how I got to that? That makes sense? Yes, no, should I go back? We're just plugging x minus m for our z-score. We're finding the z-score. We're cross-referencing it to the B column to account for this or more. We have to add the other half back to it because we're going to the end of the second half of our normal distribution here. So we're accounting for all the values from the halfway point to the curve. Do they get to the mean or higher? Does that make sense? I'm losing you. Okay. Locating proportions between two values, assuming there was a study showing the possible benefits of playing video games between study sessions on academic performance, let's say in a stats course, let's assume the following. Adult students who play video games between studying for their statistics course tend to improve 18 plus or minus 10, mean plus or minus standard deviation. Tend to improve the second time they take the exam. Assuming the data are normally distributed, what is the probability that a student who plays video games between study times will score between 12 and 30 points higher the second time he or she takes the stats exam? Step 1, x is equal to 12. To transform a raw score to a z-score, we compute a z transformation. Z equals x minus m, 12 minus 18 divided by 10. Z is equal to -0, -0.06. So we're going to find that first score, and we get 0.0239 in the B column. That's where that's from. Then we're going to add that to the second score of 30, because we're looking at the combined probability of the two different improvements. So same formula, x minus m, 18 divided by 10. Same thing we did because it was 30, because it was just a different x value. We got 1.2. We looked that up for 1.2 for this one, x is 30. We sum them together, and then it's 0.6239 that will score between 12 and 30 points higher the second time around, because we added the combined probabilities together between this one and that one. So our last one is between 14 and 32 points higher. So we can literally just take this and plug in the right information and it will still work. So we're going to assume that this is the same, our mean, and then we want to go between 14 and 32 points higher. So this is going to be 14 minus 18 divided by 10, which should be what? Is that about right? That feels right. 14 minus 18 divided by 10. Yeah, 0.4, not 0.04. Like that, right? And then we're going to, this is going to be x for 14. We're going to cross-reference it to our table. 0.4 is up here. 0.4 is 0.1554. So that's our first proportion. So we're going to add this to the second score of 32. X is 32. So same thing, 32 minus 18 divided by 10, whatever that is. 32 minus 18 divided by 10, 1.4. So we have a new z-score, 1.4. We cross-reference that. 0.4192. So we're going to take 0.4192 and we're going to add 0.1154 to that. We add those two together. Should have probability is equal to, yep. Probability is equal to 0.5746. And that's the end of that worksheet. Make sense so far? All right, let's do chapter 7. I was taking the notes on your own at this point. for probably the next couple of these. I can give you guys an assignment. I'm just concerned about the 3 more sessions and 6 more chapters. So I'm thinking worksheets would get us there quicker. But they're very thorough, so we should be good to go. So we're gonna take this and we're gonna go into chapter 7, review. Okay, we'll zoom in. So some definitions. A sampling distribution is a distribution of all sample means or sample variances that can be obtained in a sampling distribution, samples of a given size from the same population. Sampling without replacement is a method of sampling in which each participant or item selected is not replaced before the next section. This method of sampling is the most common method used in behavioral sciences. Sampling with replacement is a method of sampling in which each participant or item selected is replaced before the next selection. This method of sampling is used in the development of statistical theory. Let's find the probability of selecting a triangle marked B in the first draw to 10 other triangles. The total of 2 triangles marked B, the rest of the triangles are marked C. We would use the following formula, but first remember that P is equal to probability. P triangle marked B on the first draw, 2 out of 10, or 0.20 or 20% chance. Second draw, we do not replace a triangle marked B. If we select the triangle marked B on the first draw, then only 9 triangles remain, one of which is marked C. The probability of selecting the triangle marked C is the number of triangles marked B divided by the total number of triangles remaining on the desk. P triangle marked B on the second draw, 1 out of 9 or 0.11 or 11% chance. Now calculate on your own the following without replacement. What is the probability of selecting a circle marked D with 3 circles marked D out of a total number of 15 circles marked E? Please show your work. So we can literally think about that. So 3 circles marked D out of the total of 15. So what's the math? 3 divided by 15. 0.2. 0.20 or 20%. Make sense so far? So now, if we change it, it's going to be 2 out of 14. Because the sample space got smaller, and so did the frequency of the thing. You take 1 away from both the numerator and denominator. Does that make sense? Should I whiteboard that? Probability is equal to the frequency of the thing that you're trying to do over the sample space in chapter 5. So the first one was 3 out of 15. And these were all triangles. We took one of them away, but it affected both of them. So now it's 2 over 14 for the probability.
You wouldn't divide that 2 over the 14?
You would divide it. That would change it. Yeah.
Okay. Making sure.
Yeah, 2, yeah. I mean, I can go this direction if it makes more sense. 2 over 14, because there was a total, we have to take what we wanted to get out of the total number. The total number changed because we didn't replace it. That's why it's 2 out of 14. It affected the denominator, the total overall number. Like, say if I took the cards out and I had 51 cards now, it's going to make them both by less. So whatever 2 divided by 14 is our other one. 2 divided by 14, 0.14. Well, are we just round down 0.14 or 14%? So some more definitions. A sample design is a specific plan or protocol for how individuals will be selected or sampled from a population of interest. In theoretical sampling, the order of selected individuals matters, and each individual selected is replaced before sampling again. In experimental sampling, the order of selected individuals does not matter, and each individual selected is not replaced before selecting again. For example, a researcher selected a sample size N. Oh, this is the fun stuff. Okay. A researcher selected a sample size of N is 4 from population size of 11, N is equal to 11. Using this example, how many possible samples of 4 can be selected using experimental sampling? It's the following formula: N exclamation point N times large N minus N. Now we're going to walk through what that is. the formula when plugging the population and the sample size is the following: 11, because we had a population, so this should actually be a capital N. That would make more sense for everybody. Okay, so that's this right here is this right here, and we got it from that for the formula. Does that make sense on that formula? Now the next one, the sample size of 4, so that goes here. So we're gonna get this right here, and we're gonna plug this down here, and then we're gonna go like that right there. Does that make sense for the formula? So then we have to do n minus n. So this is going to be 11, because that's our large N from before, minus 4. Does that make sense inside the brackets? So now the breakdown is like this: 11 times every number below it all the way down to 1. That is the equivalent of this, which is the equivalent of that, which is the equivalent of this. Does that make sense? Not make sense? Okay. We're calculating. So you ever play those like games where those outcomes, those board games, and they always like where there's like clues and you have to figure something out. Remember when you were a kid? They never end the same. This is the math behind that. There's only X number of possible number of sets. It's usually not infinite, but hitting at the same time is unlikely. So whenever you have an exclamation point, it means the number you have times the number below it all the way down to 1. So n, which is the 11, right here by itself, if I string this out, this is 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Because that's the numerator, because we're trying to say, if we wanted to know how many times can we select 4 sets out of 11 numbers, well, we start with taking the population and multiplying it all the way down to 1, the largest number. Then for the denominator, after we do our numerator right here, the 4 exclamation point is 4 times 3 times 1. That's this part. We do the math, 11 minus 4, which is 7, that's left over. And then it's times 7 times 6 times 5 times 4 times 1, which is 330 number of samples possible. If it was a board game, that's a finite number of ways it would end before it would start to end the same way again. That's the math behind that. Geek out and impress your friends. So I have more for examples. What's the possibility of choosing one specific card out of a group of a deck of cards? Well, it'd be 52 cards. That's our population. And n, which would be 1 card, times 52 minus 1. So the breakdown looks like this, which actually literally equates to 52 different outcomes, which actually makes sense because 52 cards in the deck. There wouldn't be a greater outcome than the maximum number of cards. That was what the math would look like. So let's do this one together. Is the formula making sense? Like what we plug in? Yes, no? So researchers selected a sample size of 2 with a population size of 9, using this example, how many possible sample sizes of 2 can be selected using experimental sampling. So we would say n like that divided by n like that times n minus n. So it would be our 9, right? Does that make sense where that n came from? Because that's our population. That's the capital N. Yeah, you got it. And then it would be 9 again. And then 9 minus 2, which is essentially 7, right? So then if you wrote it out, it would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by all right, fine, let's write it out. So it'd be 9 times, so it'd be the same thing, 9 times 8 times 7 times 6 times like right today. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You see where the numbers came from? Did I write that wrong? Oh, I think you're right. Make sure, yeah, you're right. Small n, yeah. Which means that would actually be 2. So it would look like this. Does that make sense? 2. I typed that wrong.
So the equation is always gonna be the little n, and that, like, how
Yeah.
that is.
Mhm. And we'll not create our own.
Wait, can you go back up?
Yeah.
Where did you get the 2 part?
Right here.
But on the bottom.
So that's the formula right here. This should be a 2. It's my bad, yeah, you're right. Does anyone have a number for us? This divided by that? Eli, and I don't hold that on us. What has a number already? That's probably right. So it'd be 36 possible outcomes. So you can select 2 out of a group of 9, 36 times. In terms of how, and then what it has to do with like what numbers you would put together. Like all the different combinations of what we're talking about. How many times you select that out of that? That's, if you've done the math right, it's 36. Everyone else have 36? I haven't checked the denominator yet. That's your finite amount of pairs of 2s.
Last 4 numbers,
What was that?
you're just getting rid of those last 4.
Mhm.
She had 36, but there's 4 other numbers there, so why is it just 36?
These?
Yeah, she wrote 36 under that.
Oh, I didn't do that. This divided by this is 36 possible outcomes. I hadn't done the numerator yet. If I had divided the other big number, I would have got 36. You get 2 big numbers. I had written the first one a second ago. I can tell you, it would be this divided by whatever that is, which is probably another big number. 10,080. That's how you get 36.
Ah,
Thank you.
Sorry, it's 100,080, sorry. There you go.
That's how you get that. I can check your math. I'm just trying to be mindful of the time, but that's how you would get that. So the application is you could select a sample size of 2 from a population of 9, 36 different ways. And here's how you line up the people or the sample you're trying to figure out. Does that make sense so far? That makes sense. Okay. Some definitions and FY information to review. We have an unbiased estimator, which is any sample statistics, such as a variance, when we divide the sum of the squares, SS, divided by n/1. So SS, sum of the squares would be your numerator, n-1 would be your denominator. That's obtained from a randomly selected sample that equals the value of its respective population parameters, such as population variance on average. The central limit theorem explains that regardless of the distribution of scores in a population, the sampling distribution of sample means selected at random from that population will approach the shape of a normal distribution as the number of samples in the sampling distribution increases. FYI, the sample mean is an unbiased estimator of the value of the population mean. The central limit theorem explains that the shape of a sampling distribution of a sample means tends towards a normal distribution regardless of the distribution in the population. Theoretical sample overview. In behavioral research, we often measure a sample mean to estimate the value of a population mean. To determine how well a sample mean estimates a population mean, we need to identify a population of interest and then determine the distribution of the sample means for all possible samples of a given size that can be selected from that population. Thus, we need to construct a sampling distribution. Because statisticians use theoretical sampling to learn about the characteristics of the mean, we'll also use the sampling strategy to collect samples from the population. When you use the sampling distribution we construct to see how well the sample mean estimates the value of the population mean. To construct a sampling distribution, let us identify a hypothetical population of 5 people, n is 5, who took the Ocean personality test. You had me for Gen Psych, you probably took this. And assume that they had the following quantitative scores. Person A scored 12, person B scored 20, person C scored 7, person D scored 8, and person E scored 9. Because we know all 5 scores in the population, we can identify the mean. Then we can construct a sampling distribution of the mean to determine how the sample means we could select from this population compared to the population we calculated. So the population mean is, for n is equal to 5, is computed by adding them all together and dividing by 5, which is 11.2. That should be review, the mean. All the numbers together divided by the total number of numbers that you have, 11.2, that's our population mean. Using this, we're going to get rid of that for you guys. So using the same formula, you get a new population of students, which is 6, and they also took the Ocean personality test. Person A scored 7, person B scored 21, person C scored 5, person D scored 15, person E scored 22, and person F scored 4. And we divide all that by 6, and that will give us our population mean. And we have a number. Three. Huh. That feels about right. I can check your math.
No. That could add to it.
Yeah. And then an important implication of our central limit theorem. The central limit theorem has an important implication. It means that the probability distribution for obtaining the sample mean we go select from a population is normal. From the empirical rule, we then know at least 95% of all possible sample means we could select from a population are within 2 standard deviations of the population. And that was a condensed version of chapter 7. Actually, probably do a little bit of 8, probably okay. Change this to chapter. No, we're going to do this because that's going to make a lot more sense. We'll see if we have time for that. We probably won't. I'll probably move to next week. I'm guessing, but I'll just do it for now, just so it's easy. Okay, so chapter 8. All right. So non-directional tests. Everybody good to jump in? Do y'all know where I got that from? Chapter 8 review. Okay, this is what we would call this is an alternative hypothesis. It would be actually HO. HO is not equal to X with a null hypothesis. H sub 1 is an alternative hypothesis. Null means there's no relationship. Alternative means there's some sort of measurable relationship. That's what the difference between a null and an alternative hypothesis are. The sample size is 100, n is equal to 100. A common measure of intelligence is S intelligence, specific technical information, and G intelligence, general intelligence. We assume that specific intelligence is measured on a scale from 1 to 70, that general intelligence is measured on a scale from 1 to 90. Suppose we select a sample of college students to identify the specific or general intelligence of college students if it's significantly different than high school students. My God, let's hope so, right? You're training your brain more. In the college student population, the scores are normally distributed in general intelligence, 65 mean, plus or minus 17. In the college student population, the scores are normally distributed in specific intelligence of 32 plus or minus 20. Compute the one sample Z statistic for both the general intelligence and the specific intelligence of this population to decide whether to retain or reject the null hypothesis at a 0.05 level of significance. In this sample mean of high school students, we record a sample mean of general intelligence equal to 70, mean is 70. We record a sample mean of 54 and a specific intelligence, mean is equal to 54. The 4 steps are state the hypothesis, set the criteria, compute the test statistic, and then make a decision. So the null hypothesis is stated as a null statement about a population parameter, such as the population mean that is assumed to be true. The null hypothesis is your starting point. You will test whether the value stated in the null hypothesis is likely to be true. An alternative hypothesis is a statement that directly contradicts the null hypothesis by stating the actual value of the population parameter is less than, greater than, or not equal to the value stated in the null hypothesis. So let's determine specific intelligence in college students if it's different than high school students. First, we state the hypothesis. Null hypothesis, specific intelligence scores are equal because there's nothing's happening. They're just nothing, there's no difference. Or we can say they're not equal to 32. So something to change it to directly contradict it for alternative hypothesis. Set the criteria for the decision. The level of significance, which is 0.05, which makes the alpha level 0.05, which is a direct relation proportional to the power, which is 0.95. So we can say with 95% accuracy is what we're going for here. To locate the probability of obtaining a sample mean from a given population, we use the standard normal distribution. We'll locate the z-scores in a standard normal distribution that are the cutoffs or critical values. If you hit the critical value right on the nose or above, that's when you you reject the null hypothesis and essentially embrace the alternative hypothesis. So we will look at the z-scores for a normal distribution that are cutoffs or critical values for sample mean values with less than a 5% probability of occurrence in the value stated in the null hypothesis. So in a non-directional two-tailed hypothesis test, what we're looking for now is this is your area, this is your curve, okay? And then we're looking for cutoffs here. Inside here, this is going to be your null hypothesis. We're going to retain null hypothesis if the score is in here. If it's here, if it's right on the nose or outside, you're going to reject the null hypothesis, which basically would give you the assumption the alternative is correct. But for our vernacular, we're either going to reject or retain null hypothesis. And it's the same on both sides. We talk about a two-tailed test. These are your tails. That's what we're talking about. The shaded areas where the thing happens. So because we have a 0.05, we're going to look for a we're going to cut that in half to get 0.250 rejection in each tail. We don't know if it's where it is. We just know it's not equal. We're not sure. We're not saying it's above or below. We're just saying it's not the same. So we are going to go back into our Z table and look at student resources. Chapter 6, probability, Z-score table. So we want beyond the Z and the tail because we're looking at this. So we're looking at column C, which was 0.0250, which is right here. So we get 1.96 for our Z-score. which is our rejection region. If it hits 1.96 or higher, negatively or positively, be a negative, we are going to reject the null hypothesis. If it's below, we retain it for our math. So yeah, literally just, so that's cutoff value. Okay, so that makes sense. So the test statistic for a one sample Z test is the Z statistic. So we're going to look at the Z obtained value versus the Z score. So to calculate the Z statistic, you first compute the standard error, which is the denominator for the Z statistic. So you guys are going to need a little bit of notes here for this to make sense. Hang on. Student resources, chapter 8. Chapter 8. Table. So we have two new formulas. We have the standard error, which is this, which is equal to the standard, is the same as standard deviation, by the way, over the square root of n. And we also have the Z obtained value, which is going to be the mean minus the new mean minus the old one. So like sample mean minus population mean over the standard error. So you calculate this, then you plug it back in, and then you compare this to this, and then you know if you reject or retain the null hypothesis. So for our first one, you would take 20 divided by the square root of 100, which would be 2. Now, where do we get that from? We have our standard deviation right here. Our standard deviation. So the standard error is equal to this, which is the same as the standard deviation, which we have, which happened to be 20 divided by the square root of whatever n is, which that was 100. That's where that came from. So the standard error is equal to, that's 2. Yeah. Does that make sense? The standard error. The standard deviation divided by the square root of the sample, the square root of n. So that is, yeah, 20. That was our standard deviation was given. So this is the standard deviation right here, divided by the square root, which is n. So we're literally doing this. You can think theta or standard deviation divided by the square root of n, which happens to be 100, and this happens to be 20. So the standard error is 2. Does the standard error make sense? So then we do the Z value where we plug it in, Z obtained value, the mean, the new mean, which is going to be our sample minus our population mean over the standard error. So that's 54 minus 32 divided by 11. Where did that come from? Well, if we scroll back up, 54, that's our sample mean, minus the original 32 population mean, divided by the standard error, which was 2. Yeah. The standard error, which was 2. So we said Z is equal to the sample mean, which happens to be 54, minus the population mean, which was 32, divided by the standard error, which happened to be 2, right? Yeah, 2, which means we get 11, which means our z obtained value is equal to 11, and our z score was negative 1.9, was 1.96. So now we know it's over here. So what do? Reject the null hypothesis because it's outside, it's at the 1.96 or higher. It happens to be on this side. If it was negative 11, it'd be over here. If it was between negative 1.96 and 1.96, we would retain the null hypothesis. But because it's larger, we reject the null hypothesis for a non-directional test using the z obtained value. So z obtained value, z OBT, sample mean minus population mean over standard error. Standard error is always standard deviation divided by the square root of n, or your sample. So you always start with this, so you can plug it into that to see if your hypothesis is correct or not. Which I'm referencing this formula right here. That's where that's coming from. Which I can put up here for you guys. Standard error, standard deviation, or theta, same difference, divided by the square root of n of the sample, 1.5. 1.5, which is this, is plugged in here. Z obtained value against your z statistic that you looked up. So you plug in the new mean minus the old mean, or sample minus population mean, divided by standard error. And then you get your, it's right here, you get your z obtained value. Your z obtained value is greater than what you looked up, you reject the null hypothesis. If it's less, you retain it. And I looked it up when I first started teaching it. If it hits right on, that's where the rejection region starts. Generally, you're not going to hit this. It's either going to be above or below. I think probably every problem you're going to see. So now we have the same calculation for college students versus high school students. So we need to figure out our standard error first. So we're doing college students versus high school and general intelligence. So we have this up here. So college students and general intelligence. So we know we still have an n of 100, right? For this right here. We know we still have an n of 100. We have a standard deviation that was given to us if we go back in here. General intelligence, 17. So 17 divided by 100 is 1.7, right? Is that right? I'm sure that's right. Divided by 100. Yeah, no, it's 0.17. 0.17. So this is now our standard error of the mean. Standard deviation or theta, same difference, square root of n. So we're gonna use that 0.17. So then we do the z obtain. So then we want to look up. It would be the same 1.96 because it's a non-directional test. I looked it up before, the 0.05 divided by 2. So we're saying 0.05 because that's here and here, but it's half. So it's 0.250. So it's still 1.96 we're looking for in our table. For the z statistic, not the z obtained value. So that's where we went back into our chart here. and we found a point. 0.0250, and it's a 1.96. The only difference is we're gonna have different numbers for the z obtained value to see if it's the same or not. So the z obtained value would be it's like we did this 17, yeah, standard deviation over 100, which is the square root, which was essentially n. We got 0.17. Then we do z obtained value against the z statistic, mean minus mean over the standard. Over a standard error of the mean. Well, we can plug that in because we already have it. So we just go like, let's move it over here. 0.17. And then that was general intelligence. So we go back to what our initial mean was 65. Yeah. 65. We go here. And then our new one was 70, which was given to us. So that's 5. Divided by 0.7, which is our z obtained value. So whatever that number is will tell us to reject or retain null hypothesis. So that would be 29.41. Is that right? Yeah, 29.4. Again, large number way outside 1.96. So we would reject the null hypothesis, which means mathematically the people that are more educated are smarter. Because it's so anything above the 1.96 would work. It could be a 3. It just happens to be with the numbers that are selected in the math to be a much higher number. And that's a two-tailed test. Is that making sense? Is that starting to make sense for the formula? Not trying to rush you guys. I'm just trying to be mindful of getting through all the material in a timely fashion. There are slower lectures that are already pre-recorded. So that was that one. So some notes on directional versus non-directional tests. Non-directional two-tailed test or hypothesis test in which the alternative hypothesis is stated as not equal to a value stated in the null hypothesis. Hence, we're interested in any alternative, either side of the tail. Directional tests are one-tailed, hypothesis tests in which the alternative hypothesis is stated as greater than or less than a value stated in the null hypothesis. Hence, the researcher is interested in a specific alternative to the null hypothesis. So directional tests. Suppose our researchers were interested in looking at improving test scores among elementary students for English as a second language by offering math immersion classes in the native language of the student. In this example, the immersion courses in the language of the student should improve math scores. For this reason, an improvement being greater than, the elementary school children would see an improvement. Suppose elementary school children in the general population show math scores of 50 plus or minus 5 on any given math test, mean plus or minus standard deviation. If we select a sample of 30, there's our n, elementary school children, math immersion classes record a sample mean improvement of 60, new mean, sample, 60 points. Then compute the one sample z-test at a 0.05 level of significance. It's a one sample. It's not two-tailed, so we don't divide anymore because we're just interested in one of the tails. Does that make sense? State the hypothesis, the population mean is 50, and we are testing whether the alternative is greater than the value. Null hypothesis, there's at most 50 points in the population. It's greater than, because we're only interested in this now. It's either nothing's happened, it's either most 50 or greater than. Like it's going to match our data or it's going to be greater. So notice a key change. The null hypothesis encompasses outcomes in all directions that are opposite for the alternative hypothesis. In other words, the directional statement is incorporated into the statement of both hypotheses. In this example, the math immersion program in the speaker's native language is intended to improve math scores. Therefore, a one-tailed test is used because it is a specific expected effect. Set the criteria for the decision. The level of significance is 0.05. We go into our table. It's between 1.64 and 1.65. If you look at that, that's why. 0.0505 and 0.0495, 0.5000 is right in the center. So we're going to split the difference and make it 1.645. Like halfway. We're just going to go like 1 point over. That's our critical value of the cutoff region, that right side. We're going to compute the step statistic. So we're going to start by take 5 divided by the square root of 30, which equals 0.91. That's our standard error of the mean. Standard deviation was given to us, which was 5. That's where that came from. So that's plugging that back into this formula. 5 divided by 30, because our sample was 30. That's square root of n, 0.91. Then you will take 5 divided by the square root of 30.91. And then 60, that's our z obtained value. So new mean minus 50, population mean, divided by 0.91, 5.05, that's greater than critical value, which was the 1.96. Therefore, we know that the math and more immersion scores in native language improve the scores. The decision is to reject the null hypothesis that it didn't work. That'd be the math behind the English immersion scores. What I was thinking would be we could keep working on this worksheet together next week rather than assign it for homework. I was thinking at this point, just what we did in class and probably pre-tests through 10, just the pre-test, not the post-test. We're going to cover it. That's just a pre-test. You get all the points eventually, whether you take it once or multiple times. And then it's just the exam this week, chapters 1 through 4. And what we did in class for homework. So it's just those couple of things. So it's just the remainder of that worksheet. And then we just did in class that I recorded if you didn't, or you wanted to review that. That can certainly be due by like Sunday next week. And then I'm thinking for our plan next time would be do the worksheets for 8, 9, and 10. And take notes on the PowerPoints from like 7 through 10 on your own. Like however you all want to do that. And here's why. Then we'll have 2 more class periods to cover chapters 11 and 12 and or review things that are not clear. Otherwise, if we keep pacing out like a chapter and a half, or I'm thinking we could finish up 8, hit 9 and 10, and we'll have 2 more class periods for 2 more chapters. And the math in chapter 12, including the SPS, there's a lot of steps. We could practice it more and not feel like we're running out of time at the end because we'd have 2 more class periods for 2 more chapters besides our next one. Does that make sense? Does anyone have any concerns on really what's due? It's just what we did tonight and just do the pre-test through chapter 10 at this point. I think the post-test through chapter 7 would be appropriate, but if there's concerns raised that now we did cover chapter 7. You guys do up through post-test, chapter 7, pre-test up through chapter 10. Not worry about any post-test beyond chapter 7, because that way we can finish covering 8. We'll do 8, 9, and 10 with the worksheets, and then take your own notes on chapters 7 through 10 with the PowerPoint, or just reference them when we're doing the math, whatever's easier for you guys. Have a wonderful night. I will get this recorded and posted. Continue to reach out if you have questions or concerns along the way. That resonated for most people, right? What we did so far? Yes, I hope. I know it was a lot, just trying to be mindful